Good afternoon, I am Mr. Ish. Thank you for joining me. By now, we have gained a good amount of familiarity with regards to the Taylor series, of which when you have a function centered about 0, you have the Maclaurin series. This is a very interesting, curious case with regards to root x. If you are evaluating this function root x at a equals 0, a very interesting outcome generates f of x in regards to a power series representation. N equals 0 up to infinity, you know you have the nth order derivatives being fed in by here the value of a, which is 0, n factorial, x to the power of n, because the a is a 0. When you're looking at this, you're looking at a Maclaurin series expansion, and look what happens. When you look at the 0 order derivative of root x, it's just the original function root x. When you look at the first order derivative of root x, you have 1 over 2 root x, which you can write as you know as 1 over 2 x to the power minus 1 over 2. When you're looking at the second order derivative, you know what you have. You'll have a minus 1 over 4 x to the power minus 3 over 2. When you're looking at the third order derivative, you know you're going to have over here a 3 over 8 x to the power of minus 5 over 2, and then this is a fourth order derivative. You have over here coming out a minus 15 divided by 16 x to the power of minus 7 over 2. We'll stop right there at the fourth order derivative. A very interesting outcome comes as you start establishing your Maclaurin polynomial. The first item is not hard. Everything here, a equals 0, and now n equals 0 for the very first item. You'll have right here your 0 order derivative, you'll have a 0 come into it, you have 0 factorial x to the power of 0. The next item will be this. You can write everything here with positive exponents and bring the exponent variable down into the denominator. You'll have 1 over 2 root 0, because in all instances the derivative is being fed by your 0 value. You'll have over here x to the power of 1 divided by 1 factorial. And then the next item is this minus. You'll have minus 1 over 4. You'll have x to the power of 2 divided by root of 0, and then 2 factorial. And then you know you're coming over here as your next item, plus 3 over 8. You'll have x cubed over root 0, 3 factorial. And I don't need to write anymore, because now you're seeing something very interesting or peculiar happen. You're getting zeros here in the denominator. This right here, if you were to simplify it out, this right here is basically your series expansion. If you were to simplify it, this is a 0. But when you start looking at these items, your first, your second, third, fourth, and onwards, the nth order derivatives, you're getting undefined. You'll always have some sort of item here in the numerator. It'll be x to the power of n divided by 0. It's undefined. All of these will be undefined. Therefore, you're seeing for something like a root x type of function, there is no Maclaurin series that you can establish other than the very first item, which is 0, which is nothing, and nothing means you cannot establish a Maclaurin series. You just cannot. So that entire exercise ends. The reason for that is because if you look at a function like root x or similar type of functions which look like this, when you're looking at the derivative of this root x, what's the derivative of root x? It's the first order derivative of root x is equal to 1 over 2 root x. If you want to establish at the point 0, centering around 0, a tangent line, you cannot, because you'll be putting 0 here in your denominator. It will be undefined. You're essentially looking at something like this, which is equivalent to you looking at nth order derivatives with the 0 coming in, and you cannot do that. Everything will always be undefined. You cannot establish a tangent line over here and expect to determine a slope and an equation, because at this point you cannot establish a tangent line because of the fact that everything becomes undefined. This point is so ambiguous that you wouldn't know how to direct your tangent line. Is it vertical? Is it a certain incline? You just don't know any of that. Hence, there's no ability to generate a tangent line, let alone start developing a series at this point where the function is centered around 0. You cannot do it. And the fact that the derivatives are coming out all with the 0 value coming in as undefined shows you that to be the case. Functions which look like this don't have a Maclaurin series when they're centered around 0. If you want to establish a Taylor series for root x at 1, you can. It's not hard. Your function will be like this. You have a coming in here into your ordered derivatives. You have n factorial. You have x minus a to the power of n. But in all instances, a is equal to 1. So why don't we put a 1 over here? We'll have a 1. We'll have here a 1. And now you start expanding it. This right here would be my Taylor series expansion for root x centered around a equals 1. And it's possible. In the very first item, you're having the original function. But in all of these instances, you're always putting your 1, which is your a value. In all of these things, you're putting your 1. So the very first item will be just the root 1, which is just a 1, divided by 0 factorial x minus 1 to the power of 0. That's your first item. Your next item would be this 1 over 2 x to the minus 1 over 2, but you put 1 in place of this x, and it'll be nothing more than just a 1 over 2. You'll have x minus 1 to the power of 1 divided by 1 factorial. The next item will be this. You'll have minus 1 over 4. You'll have x minus 1 to the power of 2 divided by 2 factorial. Next item is this. Remember, in all of these exponents with regards to the 1 feeding into the x will always be equal to a 1. I'm not talking about the coefficients that are coming up over here. The next item is 3 over 8. Let's put that over here. 3 over 8. You'll have x minus 1 to the power of 3 over 3 factorial. And this last item would be here, minus 15 over 16, x minus 1 to the power of 4 divided by 4 factorial. We can simplify all of this. This would represent the Taylor series expansion of root x at a equals 1. What would it be? You start simplifying it. X minus 1 to the power of that, 1 divided by that, you just have a 1. What about this? 1 divided by 2 divided by 1 factorial is just a 1 over 2. You'll have x minus 1 to the power of 1 divided by 2. How about here? Here you'll have x minus 1 square. 4 times 2 is an 8. How about here? You'll have a plus. You will have 3 x minus 1 to the power of 3 divided by 8 times 6, 48. But 3 and 48 go into each other perfectly well. You'll have a 16. 48 divided by 3 is a 16. Last item, minus. We have over here 16 times 4 factorial, which is 24. 3 goes in that, 3 goes in that 24 item. You'll end up with x minus 1 to the power of 4. You'll have over here develop 5 over 128. 15 divided by 16 divided by 4 factorial 24. I'm getting 0.039, and that should be 5 divided by 128, 0.039. So we're good. This right here represents your Taylor series polynomial for root x, centered around a equals 1, 1, 2, 3, 4, 5 terms, but going up to n equals 4. So this here represents your TS for x. Taylor series polynomial n equals 4, because it's always n plus 1 terms. We have 5 terms, but we're going n equals 4. But you see the distinct difference between root x, where you're looking at a root x function over here at this value of 1. Here you can easily draw a tangent line, and you can easily do these type of higher order derivatives where at that specific point where a derivative exists, you can easily adjust as needed for each of these derivatives, which will come into play, these nth order derivatives, and a Taylor series establishes over here. Just know for this type of function, Maclaurin series or Taylor series cannot be established at the origin, because you have a situation where the derivatives are undefined as you put the value 0 into that derivative factor. That's what we're showing you here in this video, so keep that in mind. There are functions out there for which you can do Taylor series analysis, but you cannot do Maclaurin series. Have a good day. Bye.